All right, welcome back, everyone. You are tuning into another explainer designed specifically for the experienced automotive professional. Today, we're tackling a component that is honestly tiny in size but absolutely massive in its impact on both drivability and emissions. I'm talking about the EGR Vacuum Solenoid. Our goal today is pretty straightforward. We are going to completely master advanced EGR solenoid diagnostics so you can finally eliminate those frustrating comeback repairs. If you have ever spent hours chasing a phantom rough idle or maybe a really stubborn NOx emissions failure, yeah, you're definitely going to want to lock in for this one.
Okay, let's dive right in. Here is our diagnostic funnel for today. We'll start with core theory and PWM logic, move into component ID and failure modes, map out a logical diagnostic flow for the bay, cover bench testing, and then we'll wrap the whole thing up with maintenance and repair. Section 1, Core Theory and PWM Logic. Think of this as the bridge between the ECM and the EGR valve. This solenoid literally translates electrical commands right into physical vacuum pressure.
To pull this off, modern systems rely heavily on pulse width modulation, or PWM. Look, the ECM doesn't just awkwardly toggle the solenoid's power on and off like a light switch, right? We aren't dealing with a 1980s carburetor here. Instead, it rapidly switches the ground or power side at a very specific frequency. By varying the on-time percentage, what we call the duty cycle, from 0 all the way to 100%, the ECM achieves incredibly fine proportional vacuum control. So 50% duty cycle means the solenoid is cycling open and closed equally, delivering a moderate vacuum. This allows for precise EGR valve lift without the need for some overly complex variable valve mechanism.
Now you might be wondering, what's the actual why behind all this? Why do we need such precise vacuum modulation in the first place? Well, it's entirely about managing combustion chemistry. By exactly introducing inert exhaust gas back into the intake, we dilute the air-fuel mixture. This absorbs heat and significantly lowers those peak combustion temperatures, which is absolutely crucial because it directly suppresses the formation of harmful nitrogen oxide, or NOx emissions. If this solenoid fails, and that vacuum isn't modulated perfectly, your customer's vehicle is absolutely going to fail its emissions inspection, and they might even experience severe engine pinging or detonation under load.
The thing is, the engine computer is highly selective about when it actually commands this activation. It maps out some very specific operating conditions. The EGR solenoid is enabled only when the engine is fully warmed up, usually above 70 degrees Celsius or 158 Fahrenheit, and during light to moderate cruising loads, typically sitting between 1,000 and 3,000 RPM. Contrast that with when it's totally disabled, cold engine startups, wide open throttle where you literally need maximum oxygen, and during deceleration fuel cut. Knowing these exact parameters is super vital when you're looking at live data PIDs to confirm if the ECM is actually commanding the system on.
All right, Section 2, Component ID and Variations. Knowing what you are testing. You absolutely have to know what hardware you're dealing with, simply because not all EGR systems use the same actuation logic.
Let's compare the two primary vacuum solenoid designs you'll run into. First, the older two-port design. This is just a basic binary switch. It's either wide open or fully closed, very common on pre-1996 vehicles. But then, look at the three-port modulating design. This is your standard OBD2 proportional solenoid. It uses that PWM signal we just talked about, but crucially, it incorporates an atmospheric bleed port. This little vent bleeds off atmospheric air to rapidly drop the vacuum pressure, letting the EGR valve close quickly. If that tiny vent port gets clogged with carbon or debris, the vacuum won't release, and that EGR valve is going to hang wide open.
And this evolution in design leads us straight into modern architecture. You really need to distinguish between traditional vacuum solenoids and modern electric stepper motors. A vacuum solenoid is physically mounted externally, usually on the intake manifold for gas engines or near a dedicated vacuum pump for diesels, and it relies entirely on pneumatic hoses. But on a lot of post-2005 vehicles, engineers just eliminated the vacuum circuit altogether. They integrated an electric stepper motor directly into the EGR valve housing itself. These receive digital signals straight from the ECM with zero vacuum lines involved. Honestly, if you're hunting for a vacuum solenoid on one of these newer systems, you're going to be looking forever. Moving to Section 3, Failure Modes and Symptoms. Time to decode that drivability complaint.
So here is the really crucial point, understanding this contrast. If the solenoid fails in a stuck open state, or say that vent port is blocked, exhaust gas is just going to continuously recirculate at idle. This essentially acts like a massive internal vacuum leak of inert gas. You are going to see a crazy rough idle, stalling, poor throttle response, and on diesels you'll see a ton of black smoke.
Now, on the flip side, a stuck close failure means zero EGR flow. The engine might actually idle perfectly, but under moderate load, those combustion temperatures are going to spike, causing knocking, pinging, and a guaranteed failure on a NOx emissions test.
More often than not, the ECM is going to flag the issue before the customer even notices a symptom. Diagnostic trouble codes like P0403 for an open or shorted circuit, P0404 for range and performance, or those manufacturer-specific codes like P1403 and P1404. These point you immediately toward the electrical control circuit of the solenoid rather than a mechanical fault with the EGR valve itself. For you fleet techs out there, logging these specific P codes and standardized test results across your vehicles is a massively critical step in predicting systemic solenoid failures before they actually strand a driver.
Section 4. The logical diagnostic flow. Let's take it from the scan tool right out to physical testing. Okay, here are your first 3 rapid-fire bay checks. Number 1. Visual inspection. Look really closely at the external nylon housing for any environmental heat damage or melting from exhaust components, and definitely check those vacuum ports for carbon buildup. Number 2, grab your bidirectional scan tool, command the solenoid on, and literally listen for a distinct mechanical click. If you hear it click, the circuit is probably intact. Number 3, if there is no click, unplug the harness and measure the coil resistance with your multimeter. A healthy coil is typically going to read somewhere between 20 to 40 ohms, depending on the exact spec.
Now, if your resistance test shows an infinite reading, meaning an open circuit, or a super low reading indicating an internal short, the solenoid is completely dead. But what if the resistance is absolutely perfect and you are still throwing a circuit code? Well, that poses a really critical diagnostic question. Is the issue an internal mechanical failure where maybe the pintle is jammed with carbon, or are you actually dealing with a compromised ECM wiring harness?
To figure that out, we pivot to analyzing the live electrical signal coming from the engine computer. By hooking up an oscilloscope to the solenoid control wire, you can definitively verify if the ECM is actually transmitting that PWM signal. You are looking for a nice, clean, square wave pattern, typically running at a frequency anywhere between 25 and 100 Hz. If you just have a flat line on the scope during the correct operating conditions, well, you've just ruled out the solenoid. You are now officially hunting a wiring fault or a blown ECM driver circuit. Section 5. Bench testing and verification. Let's isolate this component on the bench.
All right, here is the definitive bench test procedure. First, pull the solenoid off the vehicle and hook a 12-volt DC power supply up to the terminals. Next, grab a manual vacuum pump, hook it to the inlet port, and pump it up to about 15 inches of mercury. Now you need to observe its behavior based on its specific design. If it's a normally closed solenoid, it should hold that vacuum completely dead tight when it's de-energized. Step 3. Energize the coil. You should hear a sharp click and the vacuum should immediately drop or transfer over to the outlet port.
And you know, this perfectly illustrates why a simple electrical test just isn't enough. You can easily have an internal electrical short where the coil windings fuse together, dropping the resistance way out of spec and risking serious damage to the ECM driver circuit. That's a purely electrical fault. But on the flip side, you could have a vacuum system leak where the internal seals fail or that nylon housing cracks. In that case, the coil might click perfectly on the bench, the resistance is totally in spec, but under pneumatic load, it just bleeds vacuum constantly. You absolutely must test both the electrical resistance and the pneumatic seal to get the full story. Finally, Section 6, Maintenance and Repair. Let's talk about the best practices to completely prevent comebacks. First off, avoid the most common installation errors that can mimic a failed component. Number 1 is reversing the vacuum inlet and outlet hoses. If you hook them up backward, the vacuum will hold against the wrong side of the internal plunger, and the whole thing just won't operate. Always label your hoses. Second, ensure proper torque and secure bracket mounting during reassembly. Excess vibration is a known solenoid killer. Third, verify your intake manifold vacuum source. Make sure you actually have that 10 to 18 inches of mercury reaching the solenoid in the first place. And lastly, never forget to clear those historical DTCs and verify the repair with the scan tool on a test drive. For those of you managing commercial high-mileage fleets, you really need to standardize a preventative maintenance and data logging schedule. Documenting these performance metrics helps track solenoid health across the entire fleet before codes even trigger. During routine tune-ups, inspect the integrity of those rubber vacuum hoses every 30,000 miles. They get super brittle from underhood heat. Take a second to confirm that those tiny atmospheric vent ports are completely clear of carbon blockages. And finally, always apply a small dab of dielectric grease to the electrical connectors during reassembly. It's a quick step, but it's absolutely critical to prevent moisture corrosion from messing with that sensitive PWM signal.
I'm going to leave you with this golden rule. Never assume an EGR valve failure before verifying the electrical and vacuum integrity of its control solenoid. It is the vital bridge between the computer and the physical mechanics. Master the solenoid and you master the whole system. So the next time you pull an EGR code, are you going to jump straight to replacing the mechanical valve, or are you going to test the electro-pneumatic bridge first?